Wow, some people don't sleep. Hmm? Sure, some people don't sleep at all. Why aren't you guys sleeping? Hmm? My goodness. People are awake, not sleeping. 31 minutes past 2, guys. Like, I mean, what's happening? Hey, we wanna learn. You're kidding me. You're kidding me. Well, yeah, so guys, I'm just actually here to do the game challenges. This is grade 12, but let's just check. Okay, I see great joy. Great joy is in grade 12, it seems. I see. You commented there. What other grades are here? I see Lucius here. I see Ice Boy here. I see not that guy. Not that guy. Okay. But I think, yeah, just to be fair to the grade 12s, I'm here to actually just go over some calculus problems. These are calculus problems that I had actually gave as game challenges. So I'm just here to do those corrections for those game challenge problems. This is differential calculus, and we are looking at differentiation rules specifically. Those who may be seeing this game challenge and they're like, but you did not teach. I did. I think it was 2 nights ago. And then what I did is I actually left these game challenge problems for people to do. So what I then want people to then do is, if you haven't seen the introductory video, I would really encourage you to go to the YouTube channel. The link is in my bio. You can check out the first video. There's a grade 12 playlist that I've created for term 2 grade 12 work. The first video was the video that basically is a follow-up to the corrections that I'm now going to be doing, and then we'll take it from there. So I'm just gonna roll with calculus at the moment. I'm gonna do these problems, then see how far we can go into calculus, the depth, the breadth, and the height of calculus. Okay, so we're looking at specifically now applying the differentiation rules. And there were a few problems that I posted here, which the first one says, differentiate the following using the differentiation rules. Okay, and that was the first problem, this one. Okay, so I'm gonna do these one at a time. And I'm guessing and I'm hoping that someone like who commented here, Great Joy, hopefully could help me out in being able to answer these questions with no difficulty at all. So the first question then is what? It says differentiate with respect to x, if y is equal to x to the power 6 over 2 plus 4 root x. There we have it. Okay, so when we differentiate that, what do we have to first do? If you remember from last time, we are going to take the function itself, y is equal to x to the power 6 over 2, and we ensure first and foremost that all variables are in the numerator. That's the first thing. So the variable here, x, which we need to differentiate with respect to, you can see it's in the numerator, okay, which is good. Then we need to make sure all roots, square roots, or roots need to be converted to exponential form. So for instance, 4 has a root x. Okay, so what we are going to then first do is x to the power 6 over 2. We'll write that as a half x to the power 6. Do you see how we did that? Okay, just so that we have a defined coefficient, which is 1 over 2, because the defined coefficient for the first term is a half, and then x to the power 6 in the numerator as well, but just the variable that accompanies the coefficient. Then we're going to say plus 4. The root x we are going to change to exponential form, and we know that since it's a square root, it means x to the power half. Okay, so do you see how smoothly I was able to do that? Because I need to ensure that before I differentiate with respect to x, all variables are in the numerator, coefficients are distinct and defined, and also all squares, roots, any roots that are there need to be converted to exponential form. Now I'm ready to differentiate. So therefore, since it said differentiate y with respect to x, I'm going to write dy over dx, and I'm going to say equal. Then differentiation must now take place. So from the function, differentiation can now take place. And when it does take place, what happens? We know that the exponent gets multiplied with the current coefficient. The variable, okay, is retained, and then we subtract 1 from the current exponent. Okay, I hope that's very clear to you. So when we differentiate, the exponent gets multiplied with the coefficient. Okay, we retain the variable x, then we subtract 1 from the current exponent. So that's what we do when we are differentiating, because we are now differentiating the function. Go on to the second term. We do the same thing to the second term. Plus positive. Then it's half times the 4, retain the x raised to the power half, we subtract 1. So that's what we constantly do. We apply the power rule. We differentiate each term, because there are how many terms in this function? There are 2 terms. Why do we know that there are 2 terms? It's because a plus and a minus sign, according to the grade 9, grade 8, grade 10 syllabus, a plus and a minus sign separates terms. So hence we differentiated this term alone, and we differentiated this term alone. How? By taking the exponent 6, multiplying it by the current coefficient, which is a half, retaining the variable x, and then subtracting 1 from the exponent. Same thing with this term. We take the exponent half, we multiply it by the current coefficient, we retain the variable x, and then we subtract 1 from the exponent half. So this is what we constantly do when we are differentiating. Then what's 6 times half? Obviously that is 3x to the power 5, no problem. Then what's half times 4? That is positive 2x to the power. Now a half minus 1 will give you a negative half. Okay, then our final answer, when we write it so that it has positive exponents. So 3x to the power 5 is perfectly fine. We have no problem with that. Plus 2. This 2 is a coefficient that is positive. This x has a negative exponent. So you remember from your exponential definitions learned in grade 9, 10, 11, you can now write x to the power half in the denominator, because the law or the definition says when a variable is raised to a negative exponent, you can change the position of the variable so it moves from the numerator to the denominator, and its exponent changes from negative to positive. So then you can actually write your final answer as 3x to the power 5 plus 2 over. Now obviously we can write this as the square root of x. That's done and dusted. That is the derivative. Okay, 3x to the power 5 plus 2 over root x. Okay, simple enough, ne? Okay, so that was problem number 1, or at least game challenge number 1. Now let's move on to game challenge number 2. dy over dx if y is equal to 3 over 2x minus x squared over 2. So the notation that we used here is going to be the same notation that we are using here, because if you look at this type of problem, okay, is that I'm an x, sis man, I'm not talking about you. What is this? What is your problem? What are you saying about me? There are people that come on in the dead of night, in the dead of mornings. So dy over dx if y is equal to 3 over 2x minus x squared over 2. So let's differentiate this. So the way that we did this one is the way that we're going to do this one. We're going to take y first. We are going to simplify it so that all variables are in the numerator, coefficients are defined, and then after we have clearly done that, then we can differentiate with respect to x. So let's go back and do what we know how to do best. So firstly, we write down the function. Y is equal to 3 over 2x minus x squared over 2. Happy days, isn't it? Then, like I said, all variables that are in the denominator must be made to be in the numerator. How? 3 over 2. This here will become 3 over 2. Coefficient is well defined, it's 3 over 2. Then this x that's in the denominator, we use the exponential definition of, we move the position of the x to the numerator and then we raise it to the negative exponent, because the x here has a positive exponent, immediately next door to the coefficient of half, right? Now these are all, now this x is in the numerator, this x is also in the numerator, but we've just made sure that we write the coefficient well defined on its own with the x combined raised to the power the exponent -1, because this x has changed its position from the denominator to the numerator. Then this here is a -half the coefficient. This x squared was already in the numerator, so it's staying in the numerator as x squared with its positive exponent. Now we are ready to differentiate. So then when we are ready to differentiate, we write dy over dx is equal to, then we showcase our differentiation. How? The -1 comes down, multiplied to the coefficient that's currently there, which is 3 over 2. We retain the x, we raise it to the current -1, and then we subtract 1 as we always do from the exponent that is there. Minus, we differentiate the second term. We do what? We have the 2 which comes down. It was positive, of course, multiplied now to the half, which is obviously half there, but remember that negative sign is to accommodate that that was already there. This 2 that came down here is positive, that half was negative, but that's still fine because that's multiplication, right? Then we retain the x, we still retain the exponent 2, we just subtract 1 from the 2. This is basically us differentiating. Then all that is left to do is multiply. So -1 times 3 over 2 is -3 over 2. All right, the x, what's -1 minus 1? It's -2. Negative times a positive is a negative, but then 2 times a half is 1. We then write x, what's 2 minus 1? That gives us 1, right? So basically our answer is definitely then what? -3 over 2. Remember that x has a negative exponent. Our final answer needs to be having positive exponents. So this x is in the numerator currently. So what do? We bring it down to the denominator. We raise it to a positive exponent. And then we say minus x. And that's it. Okay, that's it. That is the derivative. Okay, with respect to x, we get -3 over 2x squared minus x. Hey, that was nice, wasn't it? That was really nice. Okay, let's move on to the next question. The next question says, differentiate the following using the differentiation rules. Now look at this. Yes, that's it. If you look at this here, okay, the notation, take note, the derivative of x, but they've put this what in brackets. All right, so if you look at this dx is basically next to the bracket. So we are going to write it down as you are seeing it. We need to derive this expression as you are seeing it, right? So what do? As we have always done, we need to look at this expression and we need to simplify it. Simplify it. Now in grade 10, guys, when you had such an expression where you have x, you are really funny. What you could be doing right now is you could just be showering me with gifts because I'm utilizing your variable in the questions, right? That's what you can do for me. You can send me, hurt me, shower me with gifts because I am utilizing you in my platform. I am basically heralding your name to the four corners of the earth. You should be so grateful to me for actually making you famous. You know, I don't know why you are complaining. How can you be complaining when I'm using you in my life? You know, I see O'Neil K is actually doing what Mr. X should be doing for him. Thank you so much, bro. Really appreciate it, O'Neil. Really appreciate the roses too much. Oh, Nay loves joining in the fun. Thank you so much, man. You guys are amazing. Thank you. I was actually just harassing Mr. X there. Actually, I didn't. Yeah, this was just a clarion call to Mr. X. You know, he can find a sense of appreciation for what I'm doing using his name. But thank you so much, guys. O'Neil, thank you so much. And yeah, really appreciate the gifts a lot. Too much. Okay, so if we look at dx, in brackets we have x cubed plus 8 over x plus 2. So the invitation then to us is to do what? Is to simplify this first. Before we derive, we need to make sure that this is simplified. All right. So if you remember in grade 10, whenever you were given an expression of this nature, if in the numerator you could clearly see that there's a number of terms, and in the denominator there is also a number of terms, okay, then what you would do is you would look at possibly factorizing the numerator so that something in the denominator can sort of cancel out, okay? Because what we do know is we cannot, for instance, say x to the power 3 cancels with x and 8 cancels with 2. Why? Because we do not cancel across an addition or a subtraction sign. So what we know for a fact is that we cannot go ahead and just start canceling the 8 and the 2 because we don't cancel across an addition or a subtraction sign. So in our simplification, as we look at this expression in the brackets, our simplification considerations are: we need to simplify, but possibly look at numerator, factorizing the numerator if it is possible. Okay, so if we look at the numerator, is it possible to factorize the numerator? Is there anything that we are thinking about? Possibly something that we learned in grade 10 that has to do with, you know, addition, sum of cubes, right? Remember in grade 10 when we factorized a sum of cubes? Well, we need to actually apply that right now, the factorization of the sum of cubes. And remember, when we factorize sum of cubes, guys, this is basically our approach. This is what we did. So this x cubed plus 8, what we can do is we are going to take the cube root of x cubed. The cube root of x cubed, guys, is actually x. Thank you so much, O'Neil. The cube root of x cubed is x, right? So we are going to open a binomial bracket, and then we are going to open a trinomial bracket. If you remember this very well, then you will remember, oh, this is what I did in grade 10, right? So you take the cube root of what? Of x cubed, and you get x. So that means in your first binomial bracket, you'd populate your first term with the cube root of the first term. Then you take the cube root of the last term. So the cube root of 8 is 2. All right. And then whatever the sign is for that expression, that is what you would write in your bracket as well. So that means you are going to have an x plus 2 binomial bracket, okay, as part of your factors as you are trying to factorize x cubed plus 8. All right. And the fact that you can get the cube root of x cubed and you can get the cube root of 8 means indeed this is a factorizable expression because it is cubic factorization for sum of cubes. Very important. Now, moving right along, to get the 3 terms inside your trinomial bracket, what you would do is you would square. Yeah, go ahead. Wait for what do you want to clarify, Mr. O'Neil? K Radin. Okay. So what I'm saying is, first and foremost, no, this is not completing the square, guys. All right, this is not completing the square at all. This is cubic factorization. Okay, this is a cubic factorization, grade 10. Right, my grade 10 learners who have done term 1, all right, would tell you that this is cubic factorization. So if you look at the numerator, this is cubic factorization from grade 10. Okay, in grade 10 you learned a various amount of types of factorization. You did highest common factor, you did difference of two squares factorization, you did trinomial factorization, you did all sorts of types of factorization, and this one was there in the grade 10 syllabus. You see, now in grade 12 it's coming back to actually like haunt some of you, because some of you may have not, because you see, the thing is, cubic factorization is only done in the first term of grade 10, and that's it. It's never, you never see it again. All right, you never see it again until we come here. All right, sometimes in some questions that are asked in grade 11, when you're doing solve for x, sometimes it appears, but you never see it until grade 12, when you are doing calculus, when you are doing these questions. So all of a sudden it needs to be applied here, and most people forget it. Okay, that this type of factorization. So like I said, guys, this is cubic factorization, and all you do when you have cubic factorization, you just need to check your first and your second term. Your first term, you want to check if it's actually a cube. All right, and by that I mean, if you look at the variable and its exponent, right, if you were to take the cube root of whatever the first term is, does it give you a answer where you have a variable and a natural number exponent? And if you do the same thing with your second term, if you take the cube root of the second term, does it actually give you a natural number? So you see, for instance, the cube root of x cubed, it gives me x. The cube root of 8 gives me 2. And then basically whatever the sign of this particular expression is, that is going to be the sign of your binomial bracket. It's going to be positive. Okay, now I'm going to now tell you what the sign combination will be for your trinomial. You're going to have a minus sign and you're going to have a plus sign. Okay, this is normally what you then would write before you even put in the numbers. You put your plus sign for your binomial bracket, then for your trinomial bracket you put a minus sign and a plus sign. Okay, I think whilst we are still on this note, let me venture and explain to you what we would have done if it was a difference of two cubes. All right, so you would do the same thing. You take the cube root, okay, and guys, it's the cube root, right, of x cubed. So you get x for the cube root of x cubed. Then you'd also take the cube root of 8. You would get 2. All right, and then if it was minus, what you would do, you'd still open two brackets, one binomial and one trinomial. Okay, and then what you would do is you'd put a minus sign here, and you'd put a plus and a plus sign. So I just want to show you quickly. So whenever you have a sum of cubes, okay, your sign combination will be, obviously, since this was a plus sign, your binomial bracket will have a plus sign. Then it will be minus plus. Okay, so there's a change of sign here. When you have a plus sign, you have a minus plus. But whenever it is a difference of two cubes, then obviously your bracket, first bracket, will have the same sign that you have in your expression, but then your trinomial bracket will be automatically plus plus. So please, guys, just understand the signs first and foremost. Everything else is easy, and I'll explain how then you'll get your terms. Then of course here, what do you say the cube root of x cubed is? You said it's x. What's the cube root of 8? You said it's 2. Okay, so you can see, guys, that pretty much what you get in your first bracket, the cube root of x cubed is x, cube root of 8 is 2. The minus sign is the minus sign here. If you had a plus sign, what's the cube root of x cubed? It's x. Cube root of 8 is 2. And then what's the plus sign? Well, that's there. It's the same plus sign you write there. Now, you want now to actually find out what is the first term in your trinomial bracket. All you simply do is you ask yourself, x times what gives you x cubed? X times what gives you x cubed? X times what, guys? X times what gives me my x cubed there? If you want your first term, x times what gives me x cubed? So what would I write here? Exactly. Thank you, great joy. When you're bringing me great joy, that's for sure. Okay, x squared, definitely. Then for your last term in your bracket, thank you, Shelves, Debucho. 2, then 2 times what gives you 8? You see, 2 times what for your last term? 2 times what gives you 8? Exactly. 2 times what gives you 8? 2 times 4. Yes. So you're going to have a 4 for your last term in this trinomial bracket. Then guys, this one is very easy. To get your middle term, all you simply do is you take this term and you multiply them together. Guys, that's just the rule, please. If you want to ask me why, it just is the way it is. You just take the 2x and the 2. You take these two terms inside this bracket and you multiply them together. Forget about the sign. Just multiply x and 2. X times 2 gives you, and you write that in here. So x times 2 gives you, thank you, Sandile, it's 2x. Guys, I hope that wasn't too difficult, right? Okay. So this is me just reminding you of the grade 10 syllabus. In grade 10, you learned about the sum of cubes, how to factorize the sum of cubes. So I've just shown you how you factorize the sum of cubes, because some of you may have forgotten from the grade 10 syllabus how to factorize the sum of cubes. Okay, so that's how you do it. All right, let's come back here. I just want to also show you with this one. It's the same thing, guys. It's the same thing. The only difference is, obviously, since there's a minus sign for the first term, we put a minus for the binomial bracket, and then all we did was plus plus. Whereas here, with the addition of cubes, we put plus minus plus, plus minus plus. Guys, it's always the case. The sign combination will be plus minus plus if there's a sum of cubes. But if it's minus, it's going to be minus plus plus. It's always the case. Always the sign combination is like that. The first term here, same way. X times what gives you x cubed? X squared. 2 times what gives you 8? 4. And you see that the signs are taken care of. What's a negative times a positive? It gives you that negative. You see that? And then to get the middle term, you just multiply these two, forgetting about the sign. As I said, it's 2x. You see? Hi guys. Isn't this like sweet and nice and cute and beautiful and rosy and ice creamy and cute and sweet? I'm sure you guys can see that it is. I'm sure you guys have never seen a much more beautiful sight, if you know what I mean. Then remember, in the denominator we had what? Yeah. You ate that too. I'm sure. I hope you ate it as well. I hope you. It's also, you are also eating it. Great joy, and it's also bringing you great joy. You see, it's very important. When you are saying you ate that, it seems like you have a emoji of sorrow. It doesn't seem like you are happy. Great joy. So in the denominator, we had x plus 2. Remember? Yeah. Now we are ready to do what? To actually cancel and remove and say goodbye to a few entities here. Okay. Oh, you're understanding. Oh, I'm so happy. I thought, hey, I saw that face and I was like, hey, I hope that face is not a face of sorrow. So if you look at x plus 2, there we go. X plus 2 and x plus 2 now can cancel out. Why? Because, guys, we can actually cancel, because the relationship of x plus 2 and this bracket is one of multiplication divided by x plus 2. So cancellation can happen because it's not across an addition or a subtraction sign. There's one term in the numerator, there's one term in the denominator, literally. So cancellation can happen freely, and remember, we are on our way to deriving. We are not deriving yet, we are just simplifying first using factorization. We are simplifying first this expression using factorization. That's what we did. Now what are we left with? Finally, we are left with x squared minus 2x plus 4 alone, and then dx. Hey, now we are ready to derive. We are ready. You see, dx was there all along. Dx must not go anywhere, guys. Dx must stay here until the simplification process is done and dusted. Dx must not leave. Dx is there for the long ride, you know. Dx is there until he can be applied. Do not drop dx, please, guys. Whilst you are busy simplifying here and you are factorizing, dx must be there all the way for the ride. Now that you are ready to derive, guys, and derivation can happen, because you can see now you have 1, 2, 3 terms. Those 3 terms you can apply the derivative to each term. So let's go. Now you just say equal. Why do you say equal? You are saying equal because now derivation is happening. Dx disappears. You apply the derivative to the first term, to the second term, and to the third term. Are you with me? You apply the power rule. So if we derive this one, x, the 2 comes down, gets multiplied to the unseen coefficient, which is 1, but then we say x2 minus 1. You see? Minus. There's a 1 there. It's unseen, the exponent. It comes down. It gets multiplied to -2. But then we just say -2, 1 minus 1. You see? Then the derivative of a constant is equal to 0. They say the derivative of a constant number. A constant is that guy who is sleeping alone with the, just sleeping alone in the cold. Is a derivative of a constant. It has no variable, you see. So he's alone. So derivative of a constant, hey, you are a 0 when you are like that. So just write 0 there, guys. Derivative of a constant is 0. Our final answer, like Nayloves has just indicated in the comment section, beautifully said, Naylove, thank you so much, is 2x minus. We know almost that 2x to the power 0. I'm just writing this out, guys, so that you can understand. 2x to the power 0, obviously any base raised to the power 0, that variable is the only one being affected by this 0. We say 2x minus what? 2x minus 2, because x to the power 0 is 1. Okay, yeah, so that's our final answer. That is the derivative of x cubed plus 8 over x plus 2. All right, any questions? She loves, where are you lost specifically? Where specifically are you lost? You must tell me where you are lost. She loves, don't say you are lost and not tell me where. Let's try and shortcut this process so that you can tell me with your live voice. Hopefully you have a live voice. You have a live voice, or is it too much at night? People are around, you can't give me that live voice so I can hear what you are lost in. Where are you lost specifically? Because we are busy here, the dx part. Kaloku dx means we need to this means the derivative with respect to x. We want to derive with respect to x. Okay, so the question in and of itself, she loves, Debo was saying, differentiate the following using the differentiation rules, and it said dx with the bracket x cubed plus 8 over x plus 2. Right? Yeah. I love Nayloves. I think Nayloves is also helping out there with the vernacular language, vernacular tongue, and helping you out. I hope you understand though. So we need to derive with respect to x for this expression. But you see, this expression, it's a bit complicated. What needs to happen to it is that we need to simplify it first, because it's nice to derive, but it's nice to derive when things are simplified. So what we did see here is that before we even dive into deriving, because we can't derive with respect to x when this is still a bit complicated, we saw that, hey, this thing can be simplified, but how can we simplify it? We can simplify it by factorizing. How do we know that? It's because once upon a time in the grade 10 syllabus, we used to do simplification of a binomial over a binomial, So because we used to simplify the binomial over a binomial, we know that simplification of a binomial over a binomial, or many terms over many terms, means that somewhere, somehow, either the numerator or the denominator has to be factorized. So we look at the numerator, we're like, is it factorizable? Can we factorize this guy? Hey, it's possible. How? We saw cubic factorization, grade 10 concept, cubic factorization. So we went ahead and we factorized, the cubic factor, the sum of cubes here, by applying the method that I explained to you, that you need to first open two brackets, because that's what we did in grade 10. We opened two brackets, one that has two terms, the last bracket has three terms, hence I said binomial, two terms, trinomial, three terms. We took the cube root of the first term and we got x, cube root of the second term we got 2, and then we write the plus there inside. As the plus is there, we write the plus. If it was a minus, guys, it was the sum, it was the difference of cubes, we do the same thing. We write the minus as it is, we open the two brackets, we write the minus as it is, take the cube root of x cubed, the cube root of 8, we write x, we write 2. You see? So we'd have x minus 2 for the first bracket if it was minus. But since we have plus, we write x plus 2 for the first bracket. Then our signs in the bracket, that's the trinomial, okay, are always minus plus, right? I hope that makes sense. Always minus plus. Oh, I didn't see nearly Mr. Requester. Always minus plus, right?
Hi, bro. How's it?
I'm
So,
good,
what
Mr.
Nay
Oni.
is asking here, I think you have to make her understand what factorizing is.
You,
So you'll have to show her the square root or the cube root. So,
okay.
can you hear me?
Yeah, I can hear you. I can hear you, Oni. I
Yeah,
can hear you.
so what you'll have to show her is how you factorized, because I think she's lost it there.
Oh, okay. Right. No, we can. I'll do that. I'll do that then. All right.
Okay, thanks.
No problem. Thank you. Thank you for clarifying that for me. Okay. Okay. So. I think it was She Loves that was not understanding that part, the factorize or the dx part. Yeah. I know people, we are struggling with many things, eh? One thing at a time, one thing at a time. I think Neil Loves was okay. I think it would be nice if She Loves was the one that would actually just bring clarity as well to me as to what's her struggle specifically here.
Dumelang.
Dumela akhe.
Monate. Ho thwe nna ha ke understand kapa ho thwe she loves. Oh yo ke a re jo. Ke re nna ho thwe ha ke understand, nna ke understand ge. Ne ke batla clear part eo for no, nna ke understand.
Oh, okay. Oh, that's sharp. I thought it was She Loves. So it's She Loves that's saying doesn't understand.
Okay, so o tlo etsa paper 2 ntle.
What are you struggling with in paper 2, He Loves?
I think ke sharp ka analytical into le statistics le I think including geometry.
Euclidean, okay.
Yeah, the theorems ke a di tseba, but
Application.
yeah.
Okay.
I think I don't have confidence I tell you, so
I hear you.
being here will help me.
Okay. I think what I'll do is that I'll do a session tomorrow night then on that.
Around what time?
Let's say at 10 p.m.
Okay, thank you.
That'll be fine. So it's Euclid specifically, no?
Yeah, you didn't show me to that's what tricking when you're not celebrating yana ka trick.
Okay.
So you didn't show me.
Sure thing. Yeah, but Euclid is beautiful. It's lovely, that one. Eh?
Yeah, it's nice. The thing is, I fell in love with it, ne? But
Yeah.
I get to with the applications. Something. If man have a batla P, or the understand a P, ke engel ishebane le eng ke la bona jalo jalo, but then nna be ke tshaba be ke sena confidence ya go ngola ntho eo,
I hear.
and di-marks di more.
Okay. Now
Yeah.
we'll change that. We'll change that.
Oh, thank you so very much.
Sure thing. Sure.
Bye bye.
Right. All right. I think let's just get back. Yeah, this is the person here. This is the person that needs to come up here. Hello.
Hi, sir.
How are you doing?
I'm okay. How are you?
I'm doing awesome. I'm doing awesome. So I just wanted to get clarity from you. Where are you lost specifically?
How you derived?
Oh, how I derived. So the
Yes,
factorization is fine then, like you understood that.
yes, 100%.
But it's when we get here.
Exactly.
So here's the thing, when it comes to deriving, we use what we refer to as the power rule. So I'm just going to like explain the power rule. Generally
Okay.
speaking, when you have, let's say you had bx to the power n, all
Mm,
right? So when you derive, you see this exponent n.
yes.
What you do is you take that exponent and you multiply it with the current coefficient, which is b. This is just how you derive, all right? So you take this n, you multiply it with the current coefficient. So this n, where does it come from? It comes from the exponent. Are you with me? I place it there.
Yes.
I multiply it with the b that is there. The x, obviously, it is retained. Then you subtract 1 from the exponent as well. This is how you apply the power rule and therefore derive.
Oh.
So this is what I did here. What I did here, Tebogo, is that after simplifying this particular expression, the reason why I simplified it was so that I can get an expression with distinct terms, separate terms. So now that I have the terms separated, I can now apply the power rule to each individual term. So that's what I did. So
Oh,
this
yes,
x
I
squared
see.
here, you see this x squared here, I did
Mm,
this. I took the exponent 2,
mm,
multiplied it with the current coefficient, which you cannot see, which is 1. There's a invisible 1 that comes before the x most. So
yes.
that's why the 2 is there, because the 2 has been multiplied with that 1. Okay?
Mm,
Then the x was retained. The exponent 2, we subtract what? 1.
one.
Yeah, so that's me applying the power rule to x squared alone.
Okay, sir.
Then I move on to negative 2x. I do the same thing. The x variable has an exponent that is 1. You cannot see it, but it's there.
Mm,
So that 1 gets multiplied with the current number, which is negative 2, the coefficient. I get negative 2. The x is retained. The exponent that was there, which is 1, I subtract 1. You see, so I'm always subtracting 1 from these exponents.
yes.
Yes. Then there's a rule in differentiation that says the derivative of a constant number, and by constant number I mean a number that has no variable. The
Okay.
derivative of a constant is always going to give me 0.
0.
Yeah.
Oh,
So then I get 2x
oh, now it
minus
makes
2
sense.
to
I
the
just
power.
didn't understand the power rule. Now I
No
can.
problem.
Thank you so much.
No problem. No problem. I'm glad I could explain that to you. So I hope
Thank
that's fine now.
you. Yeah.
Okay. All right. No, that's powerful. Thank you. Sure. All right. Okay. So that's the power rule sorted out. Okay. Right. So we are still just finishing off these problems because, like I said, I just wanted to make sure. So if we look at the next problem, guys, the next differentiation problem. Oh, it says differentiate the following using the differentiation rule. We have fx is equal to x to the power 5 plus 3x to the power 7 minus 2x to the power negative 3 over what? Over x. So let's go ahead and do that. We have fx. What is it now, Great Joy? Why is Great Joy laughing, crying, weeping, wailing? So do we factorize every time we have square brackets? Oh, wait. Okay, I didn't see the comments there. Sorry, guys. I was zoomed in to helping out. Yes, Sandy Bell. We always subtract the 1. As do we factorize every time we have square brackets? We factorize every time Factorization can lead to simplification. This is the important thing. You see, the thing is, in grade 10 we learned that when we are given a fraction and the simplification is feasible or possible, it is feasible or possible sometimes through us factorizing the numerator and the denominator if it is factorizable. So in this case, x cubed plus 8 was factorizable. That's what could help facilitate me simplifying this particular expression. So that's why I actually used factorization to simplify. So whenever you have fractions, you have a numerous number of terms in the numerator and numerous number of terms in the denominator. You must consider factorizing, especially if you have more than 2 terms in the numerator and the denominator. Then factorization is your go-to guy, right? So let's go here. F of x is equal to, this question says f of x is equal to x to the power 5 plus 3x to the power 7 minus 2x to the power negative 3 over what? Over x. And now, you guys, when you look at this problem, you should be able to say to yourself, all right, once again, grade 10. Hey, you see grade 10 is coming up here. That's why I always tell my learners that, guys, you think that maths is independent when you are in various grades. You know, your maths will always come and sneak up on you. Things that you learned in earlier grades always come up and sneak up on you, or they will stop you from progressing where you are at if you don't know those things very well. So in this particular situation, we have x to the power 5 plus 3x to the power 7 minus 2x to the power negative 3. In the numerator, there are 3 terms. In the denominator, there's 1 term. Now, what you learned in grade 8 even and grade 9 is that when you have numerous number of terms and you have 1 in the denominator, you can actually do this. You can separate. You can separate these. You see, many terms in the denominator, one single term in the numerator, many terms in the numerator, one single term in the denominator. You can separate these. And I'm sure you guys can already see that, oh, so that means I'm going to simplify this fraction, simplify this fraction, simplify these fractions independently. Yes, because there's a common denominator. O'Neill, thank you so much. O'Neill is saying it, in that mathematical, dignified lingo, that's worthy of respect. Yes, because there's a common denominator. So you can write x to the power 5 over x, 3x to the power 7 over x, negative 2x to the power negative 3 over x. Thank you so much, Anil, for the roses. So you do that, and then, all you do again now, as you are simplifying, you just apply your laws of exponents. Or if you don't want to apply your laws of exponents, of course, you can play the cancellation game. All right. Yeah. So me, I like the laws of exponents. So when bases are the same and we are dividing, what do we do to the exponents? We keep the base, we subtract the exponents. So there's an exponent 1, it's unseen, 5 minus 1, I know what I'll get there. Then 3 over x, all right? Obviously the coefficient 3 will be there, all right? Then this x to the power 7 over x, I just write x to the power 7 minus 1. Because the bases are the same, I keep the base. When I'm dividing same bases, what do I do to the exponents? I subtract them. Minus. Good night, great joy. It was nice having you. 2. Okay, we have x to the power negative 3 and x. So we have negative 3 minus 1. Do you see that, guys? So suddenly what seems complicated is so easy. All right. Thank you, great joy. You brought great joy to my life when you were here. I really appreciate you. Thank you. Have a good one. 3x to the power 6 minus 2x to the power negative 4. Right? Okay. So there we have it, guys. Okay. And all this time, we just retain f of x because we are still in the process of doing what? Of simplifying our expression. Now, can you see, guys, I have independent what? Terms. Now, derivation can happen. I can apply the differentiation rules. So when I'm ready to do that, for f of x, I can just say f prime x. This means we are deriving. You just put this beautiful symbol, f prime x, because we are given the function as f of x. So now we are using f prime x, and we go ahead and we derive. So hopefully you guys can follow me. As you can see here, I'm just getting straight to the point. Some of you are like, huh? What's happening now? I'm getting straight to the point, guys. All right. I'm no longer doing introductory stuff. I'm getting straight to the point. 4 comes down, gets multiplied to the coefficient. The exponent, I subtract 1. That's why I have 4x to the power 3. So I'm getting straight to the point. Plus, straight to the point, 6 comes down, gets multiplied by 3. 6 times 3 is what? 18. The exponent, I subtract 1 from the 6. Okay, you see now, I nearly didn't go straight to the point. I nearly wanted to show you the subtraction. Okay, let's rewrite this. So 4x to the power 3 plus 18x to the power 5. Straight to the point, guys. Straight to the point, not messing around. Now, please be careful with this one. There's a negative 2 coefficient. There's a negative 4 exponent. The minute you bring down the negative 4 exponent and you multiply it with a negative 2, negative 2, negative 4, you multiply those together, you get a, be very careful with the signs, guys, positive 8x to the power what? Minus 4 minus 1, negative 5. Are we together? Straight to the point. But me and you don't like leaving our answers with a negative exponent. So we sort that out very quickly. 8. Remember, the x is the only one that's being affected by the negative sign. So we say 8 over x to the power 5. And there is your beautiful answer. The derivative. F prime x is equal to 4x cubed plus 18x to the power 5 plus 8x over 5. Okay. Yeah, guys, please take note that with every notation, the notation, yes, it's very easy, she loves, and I'm happy that you see that it's very easy. So with every notation, there's certain things that I do. So if I'm given the function and it says f of x, then it means I write f of x, I write equal, I simplify. I keep f of x whilst I'm busy doing what? Simplifying. All right. I keep f of x. I keep f of x until I get to the stage where it's like separate terms I can see. Then when everything has been fully simplified, then I write f prime x to show that I am deriving. So there's deriving. And then there it is. Okay. Yeah. 5, the derivative of x for the constant 5. So obviously this one will be equal to 0. Just off the bat, all right? Off the bat. Why? Because the derivative of a constant is 0. Remember, when we derive, we drop the dx and then we just write the answer. Or we derive. If there was some terms in there that had x, then we derive. Remember the song. Which song? Oh, Neil, there's a song. Neil, you must come back and tell us the song, my leader. What is the song? If there's a song, you know. O'Neill, you also strike me as the rapper kind of guy. Like, is it in the name or what? Like, in dropping some beats and stuff.
Remember your song, I Am Deriving.
Oh man, that's funny. Oh my goodness, I think I forgot my own song, man. What kind of artist am I? Ish. Ah, that is funny. Okay. All right. I thought O'Neill had some other song. Like you never know these people with their artist vibe. So yeah, you strike me as the artist kind of guy, O'Neill, especially with that name. So yeah, derivative of x, deriving with respect to x, where there's a constant, it's equal to 0. Then let's look at this last one. Oh, there. Oh, okay, I see. All right, at least you see that one, eh? Okay, and the last question that we had was derive y is equal to 7x minus 7x minus 3. Sorry, it was. Okay, so once again, if you look at the notation here, they did not say dy over dx, they just said derive y is equal to 7x minus 3. Guys, if you can see here, this is as simplified as it can get. There's two terms, so we are ready to derive here. So what we say y prime, y prime. Just exposing you also to the different notation, guys, so that you make sure that you write things in the right way. Okay, so y is equal to 7x minus 3. It's given just like that. So when we are ready to derive, you just say y prime, and then of course you know most. Okay, if I get straight to the point, y is equal to 7. I know this is going to be the derivative of a constant. Okay, if you want to really be, okay, y prime is equal to 7. Okay, because remember this one, it would be 7x 1 minus 1. All right, and then it will give us 7 there. And O'Neill has to drop the I am deriving song in the comment section all the time. Okay, oh, that's sweet. Guys, that was it, man. All I wanted to do today was just to jump on here and just kind of like help us out with the deriving. Okay, remember the question, the first one was saying dy over dx if y is equal to that, right? And remember what I said, you take the y, you deal with it, all right? Make sure that the variables are in the numerator. You make sure that the roots are converted to exponential form. And then, bam, when you have done that, you are ready to derive. And because they said dy over dx, you acclimatize to what they've said. You write dy over dx, and then the derivation happens. Okay, so in these cases I was showing step by step, but guys, as you become more fluent in doing these things, what you then do is you get straight to the point. Get straight to the point, and you won't lose any marks by going straight to the point. You'll actually be showing that you've got this. Okay, all right, guys, thank you so much. It is 3:30. I think that's just that. I'll come back on here at 10 tomorrow, Shem, for the request that was asked. I think Euclidean geometry is the pain, the pits, so I'll definitely come back here and help out with that. Nay loves, I think you can also push the paper 2 narrative. I saw someone else saying they have a problem or they have a challenge with functions, and I'm guessing, like, my question is, what aspect of functions do they have a challenge with? Because your functions, guys, that's where the goodness is. She loves the prop theorem. Will take care of that tomorrow, definitely. 10 o'clock is the time. It just means I'm going to have to forego what I was going to continue with when it comes to calculus. So I'll just put that on a hold for a little bit. I'll take that up. We'll do that prop theorem goodness. We'll propose the prop theorem, and yeah. That was great joy. Ne? Oh, snap. And she left the live. Okay, no problem. We'll see how we are able to get a hold of that. Okay, thank you guys. Thank you. Really appreciate you. Have a good one. Peace, love, joy, happiness, and all sorts. And thank you again, guys, for the gifts. Like, I really appreciate them. Like, I mean, O'Neill, my man, like, thank you so much. Like, you didn't have to, but you did, and I thank you from the bottom of my heart. Like, you have no idea how much it means to me. So thanks a ton, buddy. Thanks a ton. Please take care. Lots of love. Have a, I don't know if I could say good night to you guys. It would be like more like good morning, good night, good more night, something like that. She loves. Thank you so much as well for the roses. Oh my soul. She's loving. She's loving. She's loving. Thank you, Debo. Thanks. 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 Oh, guys. Oh. 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 Thank you. Thanks. Ah, she loves. Here you go. She loves. It's like she loves is like unleashing the love. Just like literally at the end. Thank you so much. Thank you guys. Thank you. Thank you. You're making it very hard for me to leave, you know? Stop. You must stop now because you're making it very hard for me to actually like press that button that says goodbye. I need to really leave the live. So okay, thank you guys. Thank you. See you again tomorrow, hey? Prop theorem.